afternoon, everybody. Thank you all for coming. We are Team Melinda. These are my partners, Ryan Robert and Corey Johnson. And we're here today to talk to you about our skiing robot.
The problem statement that was given to us was to build a robot that would ski down the hill successfully, avoiding obstacles like trees and other skiers. The successful robot would then be used to promote a ski competition here at Vermont Technical College.
These are a few of the requirements. Firstly, the robot should avoid objects and obstacles as it goes down the hill. Secondly, the base should not exceed an area greater than 4 square feet. And lastly, it should only need a slight push to get started and then upright at the bottom.
A problem that had to be faced and realized in our project planning was how fast our robot would go. On average, our robot moves at 10 feet per second on a moderate slope. So when an object is about 20 feet away, it has 2 seconds before it reaches that object. In those 2 seconds, it takes 1 second for the object to be seen and detected, and then another second for the robot to react. So it gives the robot 10 feet to react in time and move out of the object's way. The design concepts we use in the solutions, we're going to use accelerometers to determine the slope and the angle of the robot's base, counterweight system for balancing, a laser sensor for the vision system, legs that are similar to a scissor lift to give that action of carving, and linear actuators to control the legs. Here we have our system diagram. As you can see, we start out here with a base that has 2 linear actuators mounted to it. And then we have the scissor legs that are made out of extruded aluminum that are mounted to the skis with linear bearings and a rail. Up top we have our 12-volt battery that powers the DC motor driver and the 3KL25Z microcontrollers. Over there we have the 3 microcontrollers. The first one controls the stepper motor, which controls the vision stabilization base. The second one controls the servo motor and the LiDAR laser sensor, and it also communicates with the third microcontroller. The third microcontroller controls the DC motor driver, which then controls the linear actuators. Our original design had a counterweight mechanism on top, but through testing we found that our base was stable enough and did not need that mechanism, so we did not include it. These are our team responsibilities. Corey was in charge of vision development, Ian was in charge of vision stabilization and leg development, and I was in charge of leg control and navigation development. So here's an overview of our electrical system. We have the 3 microcontrollers. The first one is the vision stabilization board that has a built-in accelerometer and is used to control stepper motor through these 4 motor control signals. Then you have the vision board in the center that controls a servo motor with motor control signal, and it also talks to the LiDAR laser sensor with I2C communication. It also has 3 output pins sent to the navigation board. The navigation board uses those 3 inputs to make a decision and then control the motor driver, which then in return controls the 2 linear actuators.
On this slide, we have visuals of the leg subsystem. As you can see, the scissor lift legs on the bottom are attached to the linear bearings, which are mounted to skis on extruded aluminum rails. Above is the linear actuator. As it slides in and out, it creates the up and down motion to raise and lower the legs. Top middle, you can see the robot lowering one leg and making a turn. And then to the right, you can see the leg braces that were added to the center to keep the legs from folding and leaning inward. Here are some force calculations we used to determine the size of the actuator we would need. Guessing the weight forces we would need to meet. Up above, to the right, is the force calculation, weight over tangent theta. And we ended up choosing a linear actuator with 12 volt DC, 12-inch stroke, a force of 150 pounds, and a minimum speed of 1.5 inches per second.
This is a vision system, subsystem overview. As you can see in the top left, the LiDAR laser is on top of a servo motor. The LiDAR laser sends out a beam and waits for an object to be seen. It talks to the KL25Z navigation board through I2C communication, as Ryan had stated. And the servo motor also talks with the vision board in order to know where it is located for each step. The vision board then talks to the navigation board, sending out signals for each side. The LiDAR laser sensor detects an image by sending out a signal and waiting for the bounce back return. While I say wait, it's actually quite quick. It is greater than 20 milliseconds. Less than 20 milliseconds, the data is stored in a distance of centimeters, and the degree beam width is only 3 degrees, so that makes quite a bit of dead space in some of our areas. At this slide, you can see how the dead space in between each detection where it is. As the LiDAR scans, it's on a servo motor, so it starts on the left side as seen in the photo, and then it takes a reading, and if anything's there, stores the data, goes to the middle, does the same thing, and then to the right. And once this is all done, it talks to the navigation board. This is just some of the code doing just what I explained. It starts with going on the left side, staying there, waiting. It delays for a minute for the servo to get to that position, takes a reading, stores it, and moves to the middle, takes a reading, stores it, the right, same thing. And then below, once it has all the readings done in one swoop, it goes and each distance is stored in its own array, meaning that that number, like this one, is the left distance array. So if that number is over 200 for this case, which is tested, because inside we want to keep that distance lower, so that would be 2 meters. So if it's within 2 meters, it knows to go to a certain routine and then do that option. And the same for the center and the right.
The vision stabilization subsystem. This subsystem uses the KL25Z microcontroller, which is programmed to rotate the stepper motor based on what the built-in accelerometers read. For this subsystem, a gear and a modified gear were created in SOLIDWORKS and later 3D printed to be used in the stabilizing of the LiDAR laser. For the stepper motor, we decided on a 4-phase 12-volt DC unipolar stepper with 1.8 degree steps, total of 200 steps per revolution. Here's the vision stabilization accelerometer data from the y-axis on the accelerometer. We placed a line of best fit to come up with an equation that we could use to convert the accelerometer data into an angle. As you can see, the data proved to be linear and it has a high resolution. Here's some sample code from the vision stabilization system. In this first box, the microcontroller is converting the accelerometer angle into a degree. In the second box, it compares the stepper angle to the accelerometer angle and either increments or decrements it until the stepper angle is within 2 degrees of the accelerometer angle.
This is our motor driver board. It's a Scorpion XL dual motor driver. It has a left and right independent drive. It's capable of running off 5.5 to 28 volts. And it's also capable of running up to 12.5 amps continuously. This is used to control our linear actuators. It is controlled by pulse width modulation. As you can see, these are the sample pulse widths required. The motors to go forward, it requires a pulse width of 1 millisecond. The motors to stay neutral and not move at all, it requires a pulse width of 1.5 milliseconds. And for the motors to move in reverse direction, it requires a pulse width of 2 milliseconds. This is our software flowchart. So we start, everything in green on this chart is completed, everything in yellow is partially completed, and everything in red has not been completed yet. So we start out in standby. When switch 1 is pressed, we go into this navigation mode. And navigation mode is looking for an obstacle, if it's going too fast, if it's too far off the center line, and if it's close to the lodge yet. So if it detects an obstacle, it will go into the obstacle avoidance routine, which then it will avoid the obstacle and go back into navigation. If it's going too fast, it'll do an S-curve to slow down, but still continue down the mountain, down the hill. And if it detects that it's too far off the center line, too far right or too far left, it'll start to turn back until it's back in the center so it can go down the hill in the center of the hill. And if it detects that it's close to the lodge, it will apply the brakes and stop at the lodge. So this is our navigation obstacle avoidance code. So the first picture here shows that there's nothing in front of it. What it will do is go straight with turn counter. I'll explain this turn counter later on. If there's an object directly in front of it, it'll prefer to go right. If there's an object to the left, obviously it'll go right, and if there's an object to the right, it'll go left. Now say there's a wall in front of it, like the lodge, this is where we would apply the brakes, but because we do not have the brakes done yet, we have it going to the home position, which is its lowest setting, bracing for impact basically. If there's an object to the left and the right, it'll go in between them. If there's an object to the center and right, it'll go left, and center and left, it'll go right. Here is our navigation turning code. It's kind of hard to see, I guess. Up top, I'm defining the neutral, forward, and reverse pulse widths. And then we go into the turn right routine. Both motors need to go forward because one motor is mounted in the opposite direction of the other, so this causes the motion of leaning right. Then when it gets done this, it increments the turn counter. The turn counter is then used to figure out how many times you've gone right and how many times you've gone left. Same with the turn left routine. Both motors go reverse and the turn counter is then decremented. The home position, the left motor needs to go reverse and the right motor needs to go forward, lowering the robot all the way to the bottom as far as it can go. And then the go straight with turn counter routine looks at that turn counter. If it's equal to 0, then you've gone left just as many times as you've gone right, so you should be going straight, so don't do anything at all. If the turn counter is greater than 0, then you've been going right more than you have left, so turn left until that turn counter equals 0, which then means you're going straight. The same thing if you've been going left too long, you turn right. This is our electrical schematic diagram. As you can see, we have our 3 microcontrollers. To the right here, we have the vision stabilization board that has 4 outputs to the stepper motor and a power and ground. And then we have in the middle we have the vision board, which has a pulse width modulation channel to the servo motor, 2 data lines to the LiDAR laser sensor for I2C communication and power and ground, and then the 3 outputs to the navigation board. The navigation board has those 3 inputs, an input of a switch and power and ground, and then it has 2 outputs, 2 output pulse width modulation channels to the Scorpion dual motor driver, which is used to control the left motor and right motor separately. And finally, we have our 12-volt battery supply with a master switch that powers a 5-volt power supply with a switch to turn on all of the microcontrollers.
This is our scheduling and management chart. This is really helpful for finding milestones that we needed to hit. In yellow is all our milestones. One of the biggest ones was getting a prototype built of our scissor lift, because if this didn't work, we'd have to go back to the drawing board. So we built a prototype, and then we were able to see that our scissor lift actually would work, and build the actual leg system on a pair of skis that we wanted to use. Once we were able to test it on the ski hill, we then took the vision system and made it interact with the leg motion. We then put the vision system onto the skiing robot, where then we successfully made it down the hill. This is not quite done because we still have a couple bugs to work out.
These are our expenses. Start are what was supplied from the school or donated. Our most expensive parts were the linear actuators and the LiDAR laser sensor. We had a subtotal of around $820 with $310 supplied from the school. We ended up with a grand total of $581. Just a side note, for the linear actuators, there's actually a program that we can apply to, and it'll give us a pretty good discount on those parts.
This is a demonstration of our skiing robot doing S-turns on the bunny hill. As it goes down the hill, you can see it moving to the right, and then swooping back to the left, and it'll finish going back up to the right. We attached a GoPro underneath so you can really see how the actuators work. And here you can see the actuators moving as it turns right, the one on the left coming in, moving out, and the one on the right coming in. And you can see our bracing system there to help stability. And this just really helps show the movement, and we can get a good feel of how our actuators are doing. This is with the LiDAR out in the snow. This was like the last week before the snow was gone. And we were able to see here a little detection, and it moves off away from Ryan, who was standing there. You can see it move through its path, and then it comes back to the center line like Ryan was saying.
Some improvements we'd like to do. So basically, we would like to just press a button and say go to the lodge, not have to do anything else. So this could be done by mapping out a route down the hill with accelerometer data and other data, and programming that route into the robot and having it run that route every single time. A better way of doing this would be to use a GPS and plugging in the coordinates of the lodge and having it use its current navigation scheme to find its way to the lodge depending on that coordinate, and avoiding obstacles with its current system. Another thing we'd like to do is make it capable of handling a much steeper slope and have quicker movements. Now this could be done by moving the ski stance in so that it's more agile and can turn much quicker, and also by using quicker actuators to have a quicker movement. The problem with this is you're moving at a much quicker speed and you're less stable, so then we would need to incorporate that counterbalance mechanism stated